All right, welcome back. In this video, our goal is going to be graphing logarithmic functions by using transformations. We're only going to cover basic transformations, single transformations for each one of these in this video, but we're going to get very good graphs. We're also going to identify their domains, ranges, and vertical asymptotes. So on each of these first ones, I'm going to be utilizing log base 2 of x and then moving it around. So the key points that we want to identify on log base 2 of x are 1, 0, the x-intercept, and then it's always the base, comma, 1. All right, so as you can see, I've already graphed log base 2 of x. Now we need to move that around based on our transformations. So if we move over to h of x to the right, what we're going to do is that minus 3 is attached to the entire function. So what that's going to do is it's going to move everything vertically. It's going to be moving everything down because we're subtracting 3. I know on the graph paper it blends in a little bit, but that's log base 2 of x minus 3. So what I'm going to do is I'm actually going to grab this graph over here, our log base 2 of x graph, move it over so you can see exactly what's going on. We're supposed to move this all down 3 units, so I'm going to pick it up and move it down 1, 2, 3 units, and then place it back down. From here, what we're going to do is we want to identify our key points. So our key points were at 1, 0. Well, that moved down 3, so it is now at 1, negative 3. And then the other key point was at 2, 1. It's moved down 3, so it's going to be at 2, negative 2. Now the domain is going to go from 0 to infinity, but we don't actually get quite to 0. And then the range is going to be all real numbers, so from negative to positive infinity. Now the vertical asymptote was at the y-axis. It hasn't actually moved left or right, so it's still at the y-axis. So we say that's at x equals 0. Now that's a little bit different how we attach this minus 3 where it was attached to the entire function, as opposed to our next one, we have log base 2 of the quantity x minus 1. So in that case, the minus 1 is attached directly to x inside the function, so that's going to be a horizontal movement. In this case, horizontal movements kind of work the opposite direction we think they should. This is going to move everything to the right. So what I'm going to do is I'm going to pick up our graph again. This is the log base 2 of x graph, and I will move it down here just a second. Now I had identified it with the the vertical asymptote using dash lines to indicate where that is. So what's going to happen here is as we move everything to the right, that vertical asymptote is now no longer on the axis. So what we need to do is we need to utilize a vertical dash line to indicate exactly where it's at. I just included it in the original, even though it was on the axis, so that when I moved it over, we wouldn't have to draw it in additionally. So let's identify our key points. We had a key point that was at 1, 0. It's been moved to the right 1. So now, instead of being at 1, 0, it's going to be at 2, 0. Our other key point was at 2, 1. Now it's going to be at 3, 1. The domain is going to be from 1 to infinity because it's been moved over to the right. And the range is still from negative to positive infinity. Our vertical asymptote did get picked up and moved to the right 1. So now instead of being at x equals 0, it's going to be at x equals 1. All right, next up, we're trying to graph 4 multiplied by log base 2 of x. So in this case, what we're going to call this is going to be a multiple of 4. That's going to be a stretch from our original graph. When it's a number bigger than 1 being multiplied, we call it a stretch. When it's a number between 0 and 1 multiplied by the entire function, we call it a compression. So next up, we're going to grab our graph. And I'm just bringing it over this time. I don't need the right exactly. But originally, it was sitting right here. Go ahead and get rid of the right. That's not correct on this one. And let's talk about where these points have moved. This was the original log base 2 of x graph. When we multiply by a 4, what that's going to do is it's going to be multiplying the y value for each one of these key points by 4. So this one stays where it was. It was at 1, 0. So as we multiply the 0 by 4, 0 times anything is still going to give us 0. But our other key point was over here at 2, 1. As we multiply that y value by 4, it's going to go to 2, 4. So it's going to be all the way up here. So again, our key points in this case are still 1, 0, but instead of being at 2, 1, it's going to be at 2, 4. And this is going to be much taller and skinnier than the original. Still does the same sort of thing stretching this way. It's not super accurate. Could be drawing this nicer, but you'll notice it's taller, stretched out further away from the x-axis. Now, as far as the domain goes, it's still from 0 to infinity. The range is still from negative to positive infinity, and we still have a vertical asymptote. This time it hasn't been moved off of the y-axis, so it's still at x equals 0. For our next ones, we want to talk about reflections. Okay, reflections either horizontally or vertically. So in this case, I'm going to utilize log base 3 as being our base function, and that has the key points, again 1, 0, but then the base here is going to be 3, 1. I've already graphed it over here on the left-hand side. Next, what we're going to do is we're going to talk about how we attach in these negatives, where they're attached in makes a difference. If we attach a negative directly to x, things are going to move horizontally. So let's say that's reflected horizontally. So what's happening is we're moving left and right. So this point that was at 1, 0 is going to jump all the way across the y-axis, and it's going to go over to negative 1, 0. And this point that was at 3, 1 is jumping all the way across the x-axis, and it's going to go to negative 3, 1. The rest of the graph also jumps all the way across, so it's now just going to be on the left-hand side of the x-axis, and it should look like a mirror image to the original log base 3 of x graph. The domain now has changed because we get to the left, that goes off to negative infinity for an x value, and then it continues to the right up until it almost gets to the y-axis, which is at 0, an x value of 0. Now our range is going to go still from negative to positive infinity, and you're going to notice on all of these log functions, the range is always going to be negative to positive infinity. And our vertical asymptote is still at the y-axis. So we say it's at x equals 0. This is slightly different than you'll notice when we have negative out in front of the whole thing, we have negative of the log base 3 of x. This is going to be a vertical reflection. Or it's reflected vertically. So what's going to happen with our key points, referring back to the top left graph, is things are going to jump vertically and reflect about the x-axis. So this point remains where it was. This key point is still going to be at 1, 0, but the point that was at 3, 1 is going to jump over here to 3, negative 1. We're multiplying that y value by a negative. So as all of these points jump over, what's going to happen is our graph is now upside down from the original. It's going to have this sort of look going to it. So the domain still to the right of the y-axis, so 0 to infinity. The range is from negative to positive infinity. And the vertical asymptote hasn't actually moved, even though everything got flipped upside down, it's still in the exact same spot at x equals 0. Anyway, on this video, we've just covered the basics for transformations and how we attach numbers in. We may make another one here talking about exactly how to algebraically find domains and how to make transformations work when we have more than one transformation going on with logarithmic functions. All right, so hope this helped. Hit that subscribe button and you'll get these notifications whenever new videos are created. Until next time, see ya.